Okay, you'll follow along with these from your note packet in 8.1. The first example is asking us to find values for which the expression is undefined. So in other words, values that x can't be. So if we look at this expression, we know that we cannot divide by 0. All right. So if we end up plugging in a value for x, that gives us a denominator of 0. That would be a value in which it would be undefined. So to do that, we can just set the denominator equal to 0. In this case, you can either use good quad or you can factor. Set each factor equal to 0. And those represent the values that x cannot be. So in answering this question, we would say that x would be undefined when it is either 1/2 or -1, because when we plug those in, we will get a denominator of 0. We cannot divide by 0. Now, I want to point out that another way that this question could be phrased is we could just be asked for the domain of this expression. So in terms of the domain, that's going to be us answering the questions, what values can x be? All right, because we want to know where it is defined. So a way for us to say that is all reals. So x can be all reals, but it cannot equal 1/2 or -1. So again, it depends on the context of the question. If we're asked for domain, this is how we would answer it. All right. If we're asked for where it is specifically undefined, we would answer it in this format. So a little bit different, just again, depending on how the question is worded. Furthermore, for domain, we oftentimes answer our question based on an interval notation. So that is how a statement such as this would be written in interval notation. Moving on to another example. This one is unique because there is an inequality in the denominator. We know that when we are looking for domain, we're addressing the set of real numbers. In this case, with the square root and real numbers, we know we can't have a negative value underneath the square root. Furthermore, we cannot end up with 0 either. So if we were asked for values in which this is undefined, if we set x minus 5 greater than 0, that would give us right here, this gives us all the values that x can be. All right, so if x is larger than 5, we're good to go. For instance, if x was hypothetically 6, in the denominator we would have the square root of 6 minus 5, which would be the square root of 1. We can take the square root of 1. But if x is anything less than 5, we would have an issue. All right, for instance, if we plugged in 4, 4 minus 5 would give us -1. That's not a real number. So in answering the question, x is undefined for anything smaller than 5. All right. But if we, again, were asked for the domain, we would want to say x can be all reals as long as it is larger than 5. So it just depends on, again, the context of the question. Here, again, saying for domain where it can be larger than 5, but where it's undefined, it's undefined for anything smaller than 5. So it is a little bit tricky. You just got to base your answer off the wording of the question. If we were asked for domain and wanted to express it in interval notation, x greater than 5 would be from 5 to infinity. From here, we want to address simplifying rational expressions. There was a typo in example 3, number 1, that x squared should change that to a b. All right. And this says simplify using -1. What we can do here is factor out in this denominator a -1 to start. And then in the numerator, we're going to factor out a GCF. So the GCF in the numerator, we can factor out AB, which leaves us with b minus 5 left over. And in the denominator, you can factor out a negative. So the minus b squared will now become positive, and positive 25 becomes negative, so I just flip the order of that. This right here is a difference of 2 squares. So we can factor that into 2 separate factors. We still have this negative out front, but b squared minus 25 factors into b plus 5 and b minus 5. And now it's a canceling party, and the b minus 5s are invited, so we can cancel identical factors out from the numerator and denominator. That's all we can cancel out. So we would be left with an answer of AB over negative b plus 5, and we can just write that negative out front. From there, instead of just having a single expression to simplify, we can have items where we want to multiply and divide. This is no different than dividing fractions. When we divide fractions, we want to switch the problem into multiplication. So what will happen there is we will flip the numerator and denominator. All right. The first thing that I typically do is I look to see if I can simplify anything vertically. So that can't be simplified at all, the numerical or the variable part. So we don't have to do anything there. And the same here. All right. There's nothing that can be simplified within that fraction. So then what we will do is look diagonally to see if there's anything that can be canceled out. So in this case, like the a squareds can drop out. When we look at b squared and b on this diagonal, we can cancel out this b with that b squared, but there would still be a b left over in that case. The 7 and the 35, 35 divided by 7 would be 5. So we would have a 5 left over up here. So that takes care of that diagonal. The 18 over 12, 18 and 12 are both divisible by 6. So 18 divided by 6 is 3. 12 divided by 6 is 2. With the x's, I have an x in the numerator and x squared in the denominator, so this x will cancel, but we will be left with an x down here. And then the y cubed and the y, that y will cancel, but we'll be left with y squared up here. Try to be very careful with this because it's easy to forget to write something down in this next step. So as we look at that numerator, we have a 3 and a 5 that we can multiply together, so that would be 15. We still have that y squared, and then in the denominator we have 2xb. Let me clean that up.